everybody, Bill Sky, the assembly guy, and we're going to talk about a very, very confusing topic, which is called stack frames. And stack frames are a mechanism to allow assembly language programs, and actually any language, to do nested function calls, to do recursive function calls, and if it wasn't for stack frames, you wouldn't be able to do any of those kind of calls. In fact, if you compile a C program and you have it generate the assembly language listing, and that C program is calling functions, you're going to see stack frames because that's how it's done. So there's going to be a lot of lecture here, but we are going to do some coding in between. So let's get started. Okay, what is a stack frame? A stack frame, first of all, the stack is a data structure which is used by the CPU as a temporary memory storage location. In fact, I have a stack video, one or two videos behind this one, prior to this one, that really discusses the stack and how it works. So if you haven't looked at that, it might be a really good idea to take a look at it, or if you already know what a stack is, then just go ahead and continue with this video. Now, why do we have the stack? Well, because we don't have an unlimited amount of registers in the CPU, and the stack is normally used or optimized in the CPU's cache memory, which is very, very fast. So it's kind of like a nearly unlimited set of registers, but you have to use addresses instead of registers names. If we had an unlimited number of registers in the CPU, we wouldn't need the stack. Well, that's arguable, I guess, but you know, it would be you wouldn't have to use it as much. So just as a reminder, as you push things onto the stack, the address actually goes down. So right here you see a stack which has an address in it and some data, and the current stack pointer is pointing to hexadecimal 200 memory address. And when we push EAX onto the stack, notice how the memory address goes down by 8 bytes, because the width of the stack, each value in the stack takes up 8 bytes, it's 64 bits, and this is for 64-bit assembler. If you're dealing with 32-bit assembler, it's not 8 bytes, it's 4 bytes. So that address went from hexadecimal 200 down to hexadecimal 1F8, which is 8 bytes. And if we keep pushing things onto the stack, in fact, I pushed EBX and then ECX, you can see that it went from hexadecimal 1F8 to hexadecimal 1E8, which is 16 bytes. And as you take things off the stack, you pop them, and that data from the stack at that stack pointer location, in this case 1E8, goes into EAX in this case. Now notice how ECX that was in the stack, that value that was in ECX is still in the stack. So popping doesn't actually take the data off the stack, but it does copy it into the destination. And right here we're going to pop EAX, we're going to pop EAX again. You don't have to pop into the same registers that you pushed, because the values in the stack, and I show it here as ECX, EBX, and EAX, but that's really the contents of ECX, EBX, and EAX when we push it onto the stack. So when we pop them off, you can see the hexadecimal value of the stack pointer now goes up, and in this case it went up 16 bytes, which it goes from 1F8 or 1F0 to 200. So again, notice how as we pop things off the stack, the data is still in the stack. So that's really something that you want to think about. If you put the address of some password, or if you put somebody's bank account number in the stack, which is possible, and you don't clear it, you could have a security problem. There could be a hacker that could put in a virus that monitors the stack being used. In protected mode operating systems, that's very difficult, but you know, they'll find a way to do it. So you actually want to clean those out, and we're going to take a look at how to do that. So that's an overview of the stack. So what is a stack frame? A stack frame is an area of the stack, a subset of the stack that your function or your program will use. It has access to a subset of this data structure. Now, you can go into any part of the stack that you want that's available to you. Very, very dangerous, but what you do is you say, okay, here's the base of the part of the stack that I'm going to use, and then the stack pointer moves up and down as you use that, and you never go below that base pointer. And so that subset of the stack is called the stack frame. And it's defined by the base pointer, which is at the bottom. You never go below that. You never go below the base pointer. And then you've got the stack pointer that goes up and down. And then every time you create a function, that function creates its own little subset of the stack, and it stays within that range of address values. So here's how it works. When your function is called by the operating system or another function, the stack is used. What happens is automatically when you call the function, the return address of the code which called the function is placed onto the stack. So you can see right here, we've got some data on the bottom. We've got argument 1, argument 2, and we've got the return address. So what happened was when I said call this function, the return address of the line below that call was put into the stack. You can see it right there, return address, and then a base pointer is set up to be right above that return address. And that is the limit at which my function is able to use the stack. I can't go below that base pointer. Now I can access the data below that base pointer, but I would never want to change it, because if I change the return address and then when I say return from the function, it's going to return to an address that I have no business being at, that I have no business having access to, and you're going to get a segmentation fault, or even worse, the operating system could blow up. That's very unlikely these days, but it is possible. So arguments to the function are also put on the stack. If you can see right here, right above some data, I pushed argument 1 and argument 2 because arguments are passed to functions via the stack. You push them onto the stack first, and then you call the function. And we're going to see all that work out. And the stack is used to store the function's local variables as well. You can see that I have a local variable number 1. So if you remember in C or C++, if you know those languages, which I hope you do, when you create an integer, let's say, inside of the function, like int x equals 0, it's actually not allocating memory, it's actually using the stack to create that variable. So very unusual, but that's how it works. So why go through all of this? Recursive functions require a stack frame to operate correctly. Nested functions, which a recursive function is, also need stack frames to operate correctly. Using the stack for arguments and local variables, you don't need to use registers, so those can be freed up for the actual math or whatever manipulation you're doing of the data. And then since the CPU doesn't have an unlimited number of these registers, the stack is almost like a temporary set of registers that you can use to process your data. So let's actually look at the process of calling a function, and then we're going to actually do some coding to show you actually how to do it. And if you take notes and write this down and you follow along with the coding, this is it's very, very easy. It's just a set of rules that you have to abide by. There's nothing that the assembler is going to do for you. You have to abide by those rules. So as I said earlier, the stack contains data from many different processes. When a function is called, the function needs to define its portion of the stack that it will use. It needs to allocate the base pointer and then the stack pointer above it. This is what they call the stack frame. I mentioned that earlier. And when the function ends, the function needs to clean up the stack or destroy the stack before it ends. And before I forget, another name for stack frames is called activation records. I don't know where that comes from. I guess you're activating the function. But I actually like stack frames much better because it frames. You have a frame of the stack that you're using. So here we go. So we have a stack over here on the right that's pretty much empty. I mean, my main program, the base pointer is at address hexadecimal 200, and I've put some data into the stack. You know, I've done some pushes onto the stack. I'm using a little bit. And you notice how the stack pointer is above my base pointer. The stack pointer is always at a lower address. It always has a lower or equal address to the base pointer. It never has a higher address to the base pointer. That's a really important rule to remember. So before a function is called, the stack contains data from other functions, other things that you're doing in your program. Each function has a base where it cannot move below, or it should not. You can do that, but you're going to blow up the system. And that's called the base pointer. You don't want to go below that. And then each function has a top of the stack that it currently is at located, and that's the stack pointer. So you can see that's at hexadecimal 1F0. So when you call a function, the address of the line of code that from the call is placed onto the stack. So you can see right here I have a thing called IP. That's called the instruction pointer. And if you don't know, the instruction pointer is how the CPU knows where in your program you are. So in this case, the instruction pointer's value is hexadecimal 12345. A very unrealistic address, but that's what I've got for ease of this presentation. So the instruction pointer has in it the hexadecimal address 12345, and that means that the CPU is pointing to the call sum function statement. When that statement is executed, it automatically puts the address of the line of code under call sum function. It puts it onto the stack. So you can see that the line of code under 12345 is a no-op, and that is the address 12349. That's the address of the no-op. It's 12349. So if you notice on the right, the stack now has the value 12349 in it. The stack pointer has moved up the stack. It's gone down in its address by 8 bytes. And that's the mechanism at which how the operating system knows, or the CPU knows, how to get back to the function that called some function and get back to that no-op. And then you can see some function down there. When I call some function, the instruction pointer now has the address of the first line of code of the some function function. So the call actually takes the address of some function, which in this case is 98345. It simply moves that in the instruction pointer. And that's how the CPU knows, okay, the first line of code that I'm going to execute in some function is at address 98345. Very important concept to understand. Notice the base pointer hasn't changed at all. The base pointer does not change until the function creates the stack frame. And let's see how that works. So the first thing that the function needs to do is it needs to push the EBP. It needs to push the base pointer, or if you're 64-bit, which in this case we are 64-bit, you should be pushing the RBP. And that is the base pointer of the function that called that called the sum function that we're using here. So the first thing you do is you push the EBP. And when you push the EBP, first of all, notice the base pointer down at the bottom of this diagram has a hexadecimal value of 200. So you have to push that onto the stack to save it, so when your function goes back to the function that called it, like your main, it will restore that 200 into the base pointer. So as you can see, we push the RBP, or I said EBP, but it really is the RBP. We push the RBP into the stack pointer goes down in address value, it goes up, and that 200 base pointer is now placed on the stack. And as I show here, also notice, and I have to keep saying this over and over, as you add things to the stack pointer goes down in the address. Even though it goes up the stack, it goes down in the address. The next thing you do when you create a stack frame, after you push the old RBP, you put the current stack pointer's address into the RBP. That is your new base pointer. And when we do that, you can see that our new base pointer has now moved up along with the stack pointer, not above it, but at the same level. And so that's the base of our function. That is the base of our stack that our function is going to use, is the same as the stack pointer. So now the stack pointer and the base pointer are the same. Now your function can actually use the stack as it normally would. So let's say your function wants to push RAX. So it'll push RAX, and there's our RAX value in the stack, and notice the base pointer is stable. It does not change. It is the base of our stack for our function. Let's say we want to now push RBX onto the stack for some reason. You can see the stack pointer is moving up. We have the RBX value. I have a little typo there. Instead of RAX, it says EAX, but you kind of get the idea. It should be RAX in there. So we're using the stack as normal in our function. And now we can pop from the stack, we can push. You want to make sure that if you do if you do two pushes onto the stack, you want to make sure you do pops within your function. You want to clean up the stack when you're done. Now, one quick way of cleaning up the stack is simply to take the base pointer RBP and move it into the RSP. And when you do that, the stack pointer goes back to where it began when the function's stack frame was created. And there we are. We're starting to destroy our stack frame, so we move the stack pointer the same as the base pointer. Now we want to pop the old base pointer. We want to pop the old RBP out because the stack pointer is pointing to the old RBP, the old base pointer. So we pop that. Notice how the base pointer now goes back to where it was before the function began. The stack pointer is almost back to where it was before the function began. To actually make it back completely, you do a return. And what does the return do? The return statement in your function will actually pop the stack, 1, 2, 3, 4, 9 in this case. It'll put that into the instruction pointer, which will then take us back to the line of code right after the call. That's how the return works. It pops the return address off of the stack, puts it in the instruction pointer, and that's how the CPU goes back to the line of code after the call. And you can see that right there. So the instruction pointer is now pointing to the no-op that was after the call some functions, and the stack pointer is now below that address. But also notice all that old data in the stack. You might want to zero that out before the function ends. You know, having the old base pointer, having the return address there, that's not, you know, confidential data necessarily. It might be, but, you know, it's not really a problem. But that data, that old data in the stack could be a problem. So let's actually develop a simple little program with a function that uses stack frames. Let's do that next. All right, so we've got a 64-bit Linux, or it doesn't matter. You can do this on Windows. It's exactly the same process on Windows. It's not a problem. Linux is just my favorite. So we're going to create a function, and if you watch the functions, the introduction to functions in assembly language video that I did previous, this should be very simple to you. And I'm just going to do the same thing that was in my presentation that I did before this. I'm just going to say some function that creates a function. I'm going to say return. It's that simple. Now from within my code, I can actually call some function. And let's go ahead and save and build that. Okay, it looks great. Now it doesn't do anything. All some function does is return. Now, by the way, if you don't return in your function, what's going to happen is it's going to continue to execute code below the last line of code in your function, and it's going to try to execute something that might be data. It's going to execute data. That doesn't make a lot of sense. So you want to make sure you put a return. So whenever I create a function, I always put a return right there. Now, the first thing you want to do to create your stack frame, and I'm just going to put a comment in here, create the stack frame. The first thing you want to do, number one, is you want to push the RBP. Now for 32-bit, it would be a push EBP. So you want to push the RBP, and if you remember, the RBP is the function's RBP that called some function. So you want to push that, you want to save it. Then you want to move into the RBP, the RSP. And in 32-bit, this would be move EBP ESP. So by doing that, what you're doing is you're taking the stack pointer, which could be above the old RBP, and most of the times it is. You take the stack pointer, you put it into the RBP, so you can now establish that base. The RSP and the BP will be the same. So that creates your stack. And so I can do all kinds of things here. I can now push EAX, I can push EBX, you know, I can pop EBX, I can get EBX back out after I do something. You know, let's make this code a little more interesting. I'm going to move into EBX 0, and then I'll pop EBX, so we'll get that value back. Okay, so that's creating the stack frame. And I'm going to put a little comment in here, the functions code. And now let's go below that, and let's now destroy the stack. The stack frame, not the stack. You never want to destroy the stack. We'll destroy the stack frame. So to do that, to get rid of all those pushes, right? If you don't want to have to do pops for every push you did, all you have to do is you have to say move into the RSP, the RBP. And that takes the base of the stack frame and it puts that address into the RSP, which then brings them together again. So now you're basically at the same line of code here. So here is going to take you back to the state of the stack that was there. It basically does all the pops for you. It cleans up, it doesn't really clean up the stack, but it moves the stack pointer down to where it belongs. And now when that's done, you then say pop the RBP to get the base pointer of the previous function's base pointer. It gets that value, puts it back into RBP, so now you're back to where you were, and the return then grabs the return address off of the stack and puts it in the instruction pointer, so it takes us back to the line of code after the call, which in this case would be the no-op. So whenever you create a function, you should always do these 4 lines of code. This line of code right here, these 2 lines of code to create the stack frame, and then these 2 lines of code to destroy the stack frame. You know, pause the video, write those 4 lines of code, and then in between them, you actually do the job of the function, what the function it is that it's going to do. Now, you might want to do some other things. You might want to, you know, like if you're going to really be doing a lot of work with different registers, you might want to back those up. So you're going to say pop, or you're going to say push. Let's say I'm going to be using the RCX register and the RDX register a lot. So I'm going to back up those registers. And then before I pop the RBP, I'm going to say pop RDX and pop RCX, and that restores our registers. Now this actually, I don't know if this is actually, yeah, this doesn't look right. You need to do those pops before, so I'm going to do those before we destroy the stack frame. And then we did a push up here, we did a push up there, we did a pop, we need to do another pop. So I'm going to pop EAX. So now the stack is where it was before we did the, or after we did the pushes. Now we can do the pops to restore registers. So you always want to think about that. And there's some design here. You might want to get a piece of paper out and kind of draw out what the stack's going to look like to make sure you pop things out correctly. But you know, you can back up the registers you're going to use. Now, why are we backing those up? And I did those in the right order. Why are we backing those up? Because the function that called our function may actually need those registers. They may need to use those values. And if we're using those registers in here, which we're not, but if we were, actually, yeah, we're not, but if we were, we want to restore them back to what they were, so the calling function, the function that called us, doesn't get irritated because we're stepping all over their code. So let's go ahead and save and build that. And let me see. Oh, I'm using REX. This is great. This is a good error. So we're using RE. We should be using R. There we go. Love making mistakes when I teach. All right, good. So now we're not going to test this. We can. I think it would be more interesting to test it when we actually use arguments, which is what we're going to be doing next. So the next thing I want to talk about is how do you send an argument to a function? I mean, how do you do it? You could put it into a register, but we don't like to do it that way. We like to put it in the stack. So let's go over what that means. All right, I hope you liked that little demo. That's really the basis of a stack frame. So now let's take a look at how do we send arguments to a function, because we use the stack to do that. So how do we actually do that? So as a review, before you call a function, you have to, well, this isn't a review, this is how you do it. Before you call a function, you place the arguments to be sent to the function onto the stack. So let's say in this case, REX contains 100, RBX contains 200. I want to send those to the function, so what I'm going to do is I'm going to push both of those onto the stack. And the order in which I push them is pretty important. It can be a little bit confusing. We're going to see if we can get you through that. So we're going to push REX, which has 100. We're going to push RBX, which has 200. And there you go. So REX was the first thing we pushed onto the stack, which was 100. RBX, I believe it was RBX, right? Yep, RBX was the second thing that had 200. Notice how the stack pointer moves up. And now we're going to call our function. And I didn't put the addresses of these lines of code onto the presentation just because I was running out of room in the presentation. So we're going to call some function. The no-op is the line of code that's going to be pushed onto the stack. The address of that line of code is going to be pushed onto the stack so we can return. So we do the call, the return address is placed onto the stack, and then we create our stack frame. So this is the stack frame, the push RBP and the move RSP to RBP. There's the old RBP. The base pointer has now been moved up to the top with the stack pointer. And now we want to access the first argument. And the way that we're going to do that is we say move into RAX the RBP plus 24. Huh? The RBP plus 24? Well, if we look down at the stack, our first argument is that 100H, right? So if we look at the base pointer, it's 1D0. To get to that 100H, we have to add 8, then 8, then 8. What is 8 plus 8 plus 8? That's 24, because the address of the 100 is the base pointer plus 24. Yes, I know, oh my God, math. This isn't math, this is arithmetic. And the way that I learned this is I would actually draw a stack on a piece of paper. I would put each plus or minus RBP on that piece of paper, and that's how I kept track. So within RAX will contain the value 100. To access the second argument, it's kind of weird. You'd think the second argument would be a higher plus than the plus 24, but it's actually 8 bytes less because the address of the stack pointer goes down as you move things onto the stack. So now I'm going to put into RBX the RBP plus 16. How do I figure that out? The base pointer is pointing to the old RBP. I'm going to add 8 to it. That takes us to the return address. I'm going to add 8 more. That takes us to the 200. So RBP plus 16 will give us the 200, and now that's inside of RBX, is the 200. You can also modify arguments within the stack. Now, I wouldn't recommend doing this. In fact, I even said in the introduction to this video, you don't want to do this, but you can. Let's say you want to modify the argument, the second argument, which in this case is 200. You want to modify it to be 999. Well, you can do it by saying move into RBP plus 16, 999. Be very careful with this, but you can do it. You can see right here that that argument has changed to 999. Not a good idea to do that, but you can do it. Okay, once you're done with the function, you want to destroy the stack. So the stack frame. So what you do is you move the RBP to the RSP. Now here, the base pointer and the stack pointer are the same, so you might argue with me and say, well, I don't really have to do that. But it's kind of like using your turn signal on the road. If you don't do it every time, you're going to forget to do it. So just do it every time, whether there's a car behind you or not. Always move RBP into RSP just in case your function did use the stack. Now you might say, well, I know my function is not going to use the stack. Well, guess what? If you go work for a company, you're not going to be the only programmer messing with your function after it goes into production. Somebody else might have to mess with your function, but if you always destroy the stack this way, that person's not going to have to look at your code and say, why didn't they move RBP into RSP? Because I'm now using the stack. So, just avoid this problem. So you move RBP into RSP, and then what you do is you pop RBP, and then you return. And that takes us back to the main. Notice the base pointer is now at the bottom. The stack pointer is where it was before we called the function. So in your main function, you now have to pop the addresses, or you have to pop the data. You have to pop the 100 and the 200, which is now 999. You have to pop those off the stack, or you add 16 to RSP. If you add 16 to RSP, you don't have to do the pops because that looks kind of junky. So I'm going to simply add 16 to RSP, and now the stack pointer is back to where it was before you called your function. Notice, as I've said a couple of times, you still have data in the stack. So popping things doesn't remove or update the data in the stack, it just returns it when you do pops. So to clear out that data, I don't want that 999 in there, I don't want that 100. Before you destroy the stack, it's a good idea to zero out that data on the stack, which you can see I'm putting 0 in the RBP plus 16, 0 in the RBP plus 24. I'm zeroing out that data, and then I get out of this, then I destroy the stack, and now you can see those arguments are gone. Now, one thing to do, and let me go back to this, one thing that is new on this screen right here is that I'm doing a return 16. What is that? An RET 16, what is that? Well, RET 16, RET means return, 16 means free up the stack 16 bytes automatically. So if you do that, notice the stack pointer is not at the 0, 0, it's below it, because instead of that eliminated the need for your main function to pop or to move 16 to RSP. It did it for you automatically. So that is a very common thing to do, because you know your function, the function knows it's going to get 2 arguments and each argument is 8 bytes wide. You do an RET 16 or an RET 8 times 2, which is 16, and that frees up the stack. Very, very useful command to do that. So let's go ahead and demonstrate this, sending arguments to a function, and we're going to actually do some debugging here, so this will be kind of fun. All right, so we're back at our Linux program, but what I want to do is I want to create a function that actually means something. So I'm going to create a function called add2. Now I know we've done this if you watched my previous videos on functions. It's kind of a lame function, but what we're going to do is instead of adding 2 values in a register, we're going to add 2 arguments together and return them in the RAX register. So I always say return just to make sure I don't forget to do that. And the way we're going to call this function is I'm going to say move into EAX 100H, and then I'm going to push EAX. I'm going to move into EAX 200H, and I'm going to push EAX. Now you might wonder, why can't I just say push 100? Because the assembler language, the assembler won't allow you to do that. It won't assemble. And I'll show you that. If I push 100H, let's see what happens when we try to build this. You can see we get an error right here. And I keep saying EAX. Oh my goodness. So let's see if I can fix that. Oh, that's interesting. It looks like the newest version of NASM allowed you to do a push 100. In the earlier version, I believe it was version 15, it didn't allow you to do that. Wow, that's kind of nice. But just in case, we're still going to do it this way. But yeah, that's kind of nice. In fact, I'm going to pop. It should be EAX or RAX. Boy, what's wrong with my E's today? Okay, I'm going to pop RAX. And let's actually debug that. Let's make sure that works correctly. I don't trust anything. So let's go to our terminal. And let's debug this. So I'm going to right click. Oh my goodness, my mouse is all over the place here. All right. All right, so let's put a breakpoint. I'm very interested to see what RAX will be right here when we pop RAX. Because we move 200 to RAX, we push it. Now we're going to move 100 to RAX, and then we're going to go ahead and pop RAX. So RAX the 200 should be replaced with a 100 if that push worked. So there we go. So RAX right now has a value of 200. Let's step over. Oh, great. So that push of an immediate value of 100H works on Intel x86-64. That's awesome. So I did not realize it's doing that. You know something? It may have always been able to do that, but different assemblers don't. So I always like to take the most common way of doing it. Okay, so I learned something new every day. All right, that's awesome. All right, so we go ahead and we push our 2 arguments onto the stack, and now I'm going to say call add2. Now, right now, add2 doesn't do anything. But one thing to remember, the first thing I like to do is if I know that I'm going to be sending add2 2 arguments, I'm going to return 16. Because I want to clean up the stack for the main program. And that makes the main program want to use me more. If I don't do that, I have to do something like this. I have to say pop RAX to clean up the stack. Or I can say moved RSP, or no, not move, oops. I can say add RSP, 16. That's another way to clean up those arguments. But instead of doing that, I just say return 16 because each argument that I send to the function is 8 bytes wide. 8 times 2 is 16, so I do that. So there's a couple of different ways to do that. It's arguable which one is better. I think the return 16 is better because the main doesn't have to worry about it, but some of you may not agree. That's fine. It might be a thing about style. Okay, so what is add2 going to first do? Well, the first thing that add2 is going to do is going to push RBP to save the base pointer for the main function. Then it's going to move into RSP, or no, move into RBP, RSP. So that creates the stack frame. Now what we're going to do is let's clean up the stack frame. So I'm going to move into RSP, RBP, and I'm going to pop RBP. So that destroys the stack frame. Okay, now if you remember in the presentation, the arguments are going to be below the RBP pointer. So they're going to be on the stack below that. So how do we actually get those arguments? Well, if we go back to the presentation, and I think it's a really good idea to do that at this point. If we go back to the presentation, where are our arguments? Okay, here we go. So where are our arguments located? Let's take us back all the way to the beginning. Okay, so where are our arguments located? Our first argument is located 24 bytes from the RBP. And that's because we've got the old RBP here, and we've got the return address, and each one of those are 16, or 8 bytes. So 8 plus 8 is 16, plus 8 is 24. So our first argument is here on the 1, the 100 is there. That's our first argument. So we're going to say move into RAX, RBP plus 24. So let's do that. So I'm going to move into RAX, or RBP plus 24. And then I'm going to say add RAX RBP plus 16. Why am I doing that? Because the second argument is located at 16. RBP plus 16. Our 200 is located 8 bytes above the 100, our first argument, which is 8 bytes less than our first argument's address. So let's go ahead and do that. So we add it. And actually, let's build it at this point and make sure it's okay. Yep, it looks good. So it takes our first argument, move our first argument into RAX, add our second argument to RAX. Now, one thing you could have done is you could have said move into RCX, RBP plus 16, and then you could have said add RCX to RAX. That's perfectly fine. But if you do that, you're modifying the value of RCX, right? You're modifying that value. And if the main function that called you is using RCX, oops, you're overriding their data. So if you decide to do that, you want to make sure that you push RCX right before you use it. Now, here's the thing, is because our push only affects the stack pointer, it's not going to affect the base pointer, so your base pointer code doesn't have to change. That's why we use the base pointer instead of the stack pointer. The base pointer never changes within your function, or it shouldn't until the function is ready to end. And then right before you destroy your stack pointer, you say pop RCX to restore it for the main function. And we're going to leave it like that for right now. All right, so let's save and build that. Looks good. Let's debug it. Oh, we don't do make. We say kdbg. All right, so let's display the stuff, and we're going to look at the stack. It's going to be kind of fun. We're going to look at the stack to see what it looks like. Okay, so I'm going to put a breakpoint right here, and I'm going to run our program. Okay, so I'm going to move 100 into RAX. I'm going to push RAX onto the stack. Now, how do you know what the stack looks like? Well, the stack pointer is this number down here. It's RSP. So that happens to be 7 and 1, 2, 3, 4, 5, 6, 7 Fs. So it's 7 Fs DF80. All right, so let's go to memory. 7 Fs DF80. So I'm going to say 0x 7 Fs 1, 2, 3, 4, 5, 6, 7 DF80, I believe. And here we go. So that is where our current stack pointer is located. And notice the number 1 in there. Okay, that, I don't know what that is. That might be the, I'm not sure what that is. I have to look at it a little bit. So anyway, so that is the stack pointer. Now I'm going to step over. It's going to push RAX. Now remember, RAX has 100 in it. Now nothing changed in your memory, and the reason it didn't change is because the stack pointer has just changed its value because we pushed something. The stack pointer has become 8 bytes smaller. So now it's DF78. So let's go in here. Instead of DF80, let's say DF78. There's our 100. There is the 100 that we pushed onto the stack. Now, right now, we're looking at these as 4 bytes. I'm going to go and look at these as 8 bytes, and we can now see our 100. So that's the 100 that came out of RAX, which was 100. Pretty cool. Now we're going to move 200 into RAX. So we're going to say step over. We're going to push RAX. So I'm going to go over to registers, and the stack pointer is now DF70. So let's put DF70. And there's our 200. So there's our 2 arguments that we're going to send to our function. Pretty cool. They're on the stack. So now let's call add 2, and I'm going to click step into this time. Now let's take a look at the stack. So I'm going to go into registers. The stack pointer is now DF68. So I'm going to type DF68, and let's take a look what the stack pointer looks like. Well, here's our 200. That's our second argument. Here's our 100. What is this right here? That is the address of the line of code below the call. And what is the line of code below the call? It's a no-op. Now, how do we know that for sure? Well, it's 401.017. So I'm going to do this. I'm going to say 401.017. And I'm going to right-click on this, and I'm going to look at it as bytes. You see that 90? That is what a no-op is. That is the machine code for a no-op, a 90. So the address 401.017 is the program code pointer that takes you to that no-op 90. I just think that's pretty cool, is that we are now looking at the code 90, the next line of code, which is the move 60 to RAX, is this B8 here. I believe it is. But yeah, it's pretty neat that we are actually moving, or we can actually see our code in the memory display. So now let's go back to our stack pointer. And that's what 401.017 is. So that's the return address. Okay, now we're going to push RBP. And we can go ahead and put 60 there. The old RBP is 0, the 0 address. So that was the mains RBP. We're going to move RSP to RBP. And then we're going to push RCX. Let's change this to 58. And RCX happened to have a value of 0 in it. So that's why it's there. Then we're going to move RBP plus 24 to RAX. Now let's look at our registers. Remember, our first argument was 100. So there's 100 in RAX. We're now going to move 200 into RCX. RCX is 200. We're going to add RCX to RAX. RAX now has 300. We're now going to pop RCX to restore it. It's now 0 again. Now we're going to clean up our stack. And we're back at the line of code underneath the call, which happens to be a no-op. The return value is 300. If you watched my functions, introduction to functions video, you will have seen that RAX or EAX in 32-bit always contains the return value. We're not returning 16. Return 16, RET16 simply means clean up 2 entries on the stack. So there we go. So we've got our very first function that actually does something. Now, if you want to see if the function works and doesn't give you a segmentation fault, don't debug it. Just say /main, and it worked great. Now, if you were using the functions template to write this code, you could push RAX and then call my print 64-bit num hex or decimal, and then print end-L, and you could actually print it on the screen, so you wouldn't have to debug it. So there you go. Our first program, our first function that contains arguments sent to that function and how you access them. All right, the last thing I want to do in this video is talk about this idea of local variables. I mentioned this earlier. How do you actually allocate a local variable in your function using the stack frame? Well, let's get there first. So what we're going to do is we're going to push a couple of arguments onto the stack like we did in our last coding demo. Then we're going to call some function, and let's take a look at what the stack looks like as we call our function. So the first thing you need to do is you need to create your stack frame, and then to create one local argument you subtract 8. Now if you're on 32-bit, you subtract 4. So you subtract 8 from the RSP, which is the stack pointer, and now you have your local argument. How do you put data in that local argument? Well, instead of adding 16 or adding 8 to, or adding 24 to your RBP, you subtract 8 from it. Because remember, the stack pointer's address is smaller as you go up, as you add things. So what we're going to do is, in this case, we're going to move 99 hexadecimal into our local variable, and there it is. You can grab it and move it into your stack. So that's our local variable, RBP minus 8. You can also read the data from your local variable. In this case, I'm going to put it into RAX. So I'm going to say move into RAX RBP minus 8. And there it is. It's in my RAX register. So now you can destroy the stack. You just move RBP to RSP. Actually, yes, that's it. Move RSP to RBP to RSP, sorry. Pop RBP and return 16. Why are we returning 16? Because we sent 2 arguments to the function. And there we are. So again, we still have that local variable in there. You might want to zero that out. And the way you can zero that out is you can say move into RBP minus 8, 0. Like we moved 99 in there, you can move 0 in it. That will zero it out. So it's a really good idea to zero out all of your stack contents. You don't want to zero out the old RBP. You don't want to zero out the return address. But you definitely may want to zero out some things in the stack frame, your local variables, in case you've got some confidential data in there. A password, a pointer to a password, a quantity, something like that. You want to zero that out. So same problems as when we sent arguments. So that's it. You use minus instead of plus. Let's do a quick little coding demo on that. Okay, so this is the same code that we did in the second coding demo from this video. Let's go ahead and create a local variable inside of our function. And the way that I'm going to do that, now this gets kind of weird when you're dealing with when you've pushed things. You really, inside your function, you really have to draw this up on a piece of paper as to how you would do this. So to avoid that complexity right now, I'm going to actually go ahead and just get rid of that backup. And instead of doing this move 16, I'm just going to say add RBP plus 16. So it's really a good idea not to use registers unless you absolutely have to use them. And if you do, you have to kind of draw it up to figure out, where your local variables are going to be. So, but for right now, so let's go ahead and create a local variable. So the way I'm going to do that, I'm going to say subtract RSP comma 8. That is going to be our first local variable. And I'm going to call, that's going to be RBP minus 8. And I do that all the time, where I will actually write in my comments what the address is of that local variable, so I know in my code where I can get it. And I'm going to subtract more. I'm going to subtract another one. So I'm going to create my second local variable. And that's going to be RBP minus 16. So some little coding, some little comment hints to help you with your coding. Okay, so what I want to do is I want to move the arguments into local variables before I add them together. Kind of weird. You probably wouldn't do this. You would just keep it like this. But we're learning, right? We're not actually doing something that necessarily makes sense. So I'm going to move my first local variable. So I'm going to say move. Now, where's my first local variable? It's RBP minus 8. I'm going to move into RBP minus 8, RBP plus 24. So that's going to move our first argument into our first local variable. And let's see if that'll work. Now that might not work because you might not be able to move things from memory to memory. You might have to actually put them into a register first. And that's what it's telling me right here. You can't actually do that. So what we're going to do is we're going to move that into RAX. Again, it doesn't make a lot of sense to do this, but we're learning, right? So we're going to move our first argument, and then we're going to say move, and our first argument, or our first local variable is RBP minus 8. I'm going to move into RBP minus 8, RAX. And that should work. Okay, great. Notice we're not backing up RAX because whenever you call a function, you should assume that function is going to destroy RAX. So that's why we're doing that. Okay, so now I want to move our second argument into our second local variable. So our second argument, as you can see right here, is RBP plus 16. And we're going to move that into our second local variable, which is RBP minus 16. And move our second argument into our second local variable. Make sure that builds okay. All right, looks great. Now let's go ahead and make sure that all works. Let's make sure that our local variables have the right data in them. Remember, our first local variable should have 100. Our second local variable should have 200. And how are we going to figure that out? Well, it's pretty easy. I'm going to move into RAX 0. Then I'm going to move into RAX, our first local variable, which is RBP minus 8. Now, how did I know that so quickly? I put it in my comments. That's how I knew it, looked at it so quickly. I looked up at that code. All right, so now I'm going to move into RAX, RBP minus 16. Again, how did I know that? It's up here documented. Those comments are so useful. All right, so let's save and build that. All right, let's debug it. And what we're going to do is we're going to just put a breakpoint right here on our move RAX RBP minus 8 to make this debugging quick. So let's do the main first to make sure we don't have any segmentation faults. Okay, so it looks like the code isn't doing anything weird that we know of yet. We have to test it here. All right, so I'm going to turn off this breakpoint. I'm going to go down into my add to, and as I promised, I'm going to put a breakpoint right there to make sure our local variables are working. So I'm going to run this. Okay, so RAX has the values there. Now remember, our first argument was 100. We put that into our first local variable. There's what I think is our first local variable. Is it? It is. It's 100. So we were able to put the first argument into our first local variable. Let's take a look at RAX now when we grab it from our second local variable, 200. It worked. Awesome. Now I always like to make sure that my code has not my new code has not messed up my old code. It didn't, so we're okay. Let's make sure we return okay. Awesome. So that is putting local variables in your function and then using them. This was kind of a silly example, but I think it brings home the point. All right. That was great. I love stack frames. I love looking at memory. I love looking at the stack. It's pretty cool. So in summary, within your function, you will always use the RBP and or EBP for 32-bit registers as the starting point when accessing local variables. Why? Because RBP, EBP must never change within your functions. You never change it until you're ready to leave your function and destroy the stack frame. So arguments are always going to be at RBP plus n, and n is equal to the argument number. Well, it's more to that, right? It's RBP plus 16, which includes the old RBP and the return address. So it'll be plus 16. And then n, then you'll add n to that. And n is actually the argument number times 8. That's not quite right, but you get the idea. Take a look at the previous part of this video to actually see those numbers. And then to access local variables, you always say minus some value n. So local variables will always be above the EBP or RBP. Arguments will always be below it. You'll always use multiples of 8 to access storage stack locations in 64-bit. In 32-bit, you'll use 4 instead of 8. Sorry. In 32-bit, as a reminder, you use ESP as the stack pointer and EBP as the base pointer. In 64-bit, you use RSP as the stack pointer and RBP as the base pointer. Okay, so boy, that was a long video. That was a lot of information. When, I wish I had videos like this when I was learning. Go ahead, rewatch it, code along with me. That's the best way to learn this stuff. That's the way you become expert in stack frames. Hope to see you in our next video.